Hello, welcome to my talk on an easy way to derive the Bernoulli's equation. After the talks on the streamlines and how we can build the streamline equations and its combination with the Euler equation would provide us an easy way to derive the Bernoulli's equation. So in this talk, I will talk a historic introduction of Bernoulli's principle and the equation. And I will talk about the assumptions for Bernoulli's equation. And then I will introduce the streamline equation and the Euler equation. Then the derivation of the conventional Bernoulli's equation, step-by-step derivation. And lastly, I will give two simple examples in applying the Bernoulli's equation. As we know, all fluids are viscous. However, the Bernoulli's equation is only for inviscid flow. Thus, we have a question: can the real fluids be taken as inviscid? To answer this question, we can see the list of the common fluids. Here we have air, water, milk, cream, oil, tomato juice, honey, mayonnaise, sour cream. And in this column, the fluid viscosity mu is given. So this is the typical definition to define the absolute viscosity effect for the fluid. If mu is large, that means the fluid would be more sticky. And if we look at the common fluids, air and water, their viscosities are quite small. And in fluid dynamics, we are more talking about the kinematic viscosity nu. It is defined as the viscosity divided by the density. So it is a relative viscosity, but it is an important factor in the fluid dynamics. So now, the kinematic viscosity, we can see the water has the lowest kinematic viscosity, so as the air. Here in this table, only milk has lower kinematic viscosity than the air. And we can see like honey, mayonnaise, and sour cream would have much larger, more than 2,000 times than water. So these are the very sticky fluids. Now, from this table, we can answer the question: can the real fluids be taken as inviscid flow? The answer is yes, because the most common fluids, the air and the water, both have very small viscosity, the kinematic viscosity. So in many applications, they can be taken as inviscid flow and the potential flow in many practical problems. This is why the Bernoulli's equation is so useful in many practical applications. Bernoulli's equation is an integral form of Euler equation. We can apply the Bernoulli's equation for the pipe flows, and we can also add the modifications for the losses in the pipe flow because of the viscosity of the fluids. And if we have pumps and turbines, we can also add the modifications to the Bernoulli's equation. Bernoulli's equation is also used for Petri tube and Venturi tube, which are used for measuring flow velocity and flow rate. these are still widely used. And the Bernoulli's equation is also used for the flow past the airfoil, hydrofoil, and airplane, and in the wave structure interactions, etc. The way to solve the practical problem in fluids using Bernoulli's equation, we use continuity equation or Laplace equation to get the fluid velocity field. And we can also see for some simple problem that analytic solutions are possible. And then we apply the Bernoulli's equation for calculating the pressure in the flow field. Daniel Bernoulli was the first one who initialized the pressure-velocity relation in the fluid dynamics. In 1738, he published his book Hydrodynamica, in which the Bernoulli's principle was published. Pressure decreases when the fluid speed increases, and this is the plot he drew in his book. And his father, Johann Bernoulli, also studied the Bernoulli's principle. Both then studied the pressure-velocity relation for some simple 1D flows. But the generalized Bernoulli's equation was actually derived by Euler in 1752. See the next slide. In 1752, Leonhard Euler derived the generalized Bernoulli's equation, as we have seen in many textbooks, which is in a form given as this. This is the term calculated with the fluid velocity, this is the pressure, and this is the term due to the height in the fluid. And these three terms together would be a constant. Here C0 is an integral constant. It depends on different situations. The Bernoulli's equation also means the sum of these three terms is a constant along a streamline. Now we regard the Bernoulli's equation as an integral form of Euler equation. However, this might not be the case for the Euler who derived and published the Bernoulli's equation, as well as Euler equation. However, the publishing date would be different. Bernoulli's equation first in 1752 and the Euler equation later in 1757. I tried to find how Euler derived the Bernoulli's equation, but unfortunately I can't find the information. So the derivation of Bernoulli's equation in this talk would be referred to some textbook. As in the most textbook, the generalized Bernoulli's equation is under the following assumptions. The first assumption is flow is inviscid. That is, there will be no viscous force within the fluid. The mathematical expression for this is the fluid viscosity mu is 0. The second assumption is the flow is steady. That is, in the Euler representation, the local velocity is independent of time. That is, the velocity at a given or fixed spatial location is a constant. The expression for the steady flow is given by the partial differentiation of the velocity vector v with regard to t is 0. However, for Bernoulli's equation, we might have some exception. One exception is for potential flows. The unsteady Bernoulli's equation is possible, such as those in the wave structure interactions based on the potential flow theory. The third assumption is the body force acting on the fluid must be conservative. The most applied body force in the fluid is the fluid gravitational force, which is a conservative force. That means the body force per mass is given as this, so the gradient of the function gz is given as this. Here we can see when we calculate the gradient of the function gz, it is calculated as this. Obviously, we can see gz is independent of x, so this term would be 0. And gz is independent of y, so this term would be 0 too. Thus, the only term left is this, so this will be calculated as this because of the gravitational acceleration g is a constant. The fourth assumption here is the fluid is incompressible. This is the assumption for the fluid of low speed. If the fluid is incompressible, that means the fluid density would be a constant. And we can also have an exception for this assumption. Since in very high speed flows, such as the flows past the transonic and supersonic airplanes, the Bernoulli's equation can be derived for compressible flows if the ideal gas equation can be used. We will see this in different talk, but here for the simplicity of the derivation of Bernoulli's equation, the density of the fluid is assumed as incompressible. And for the general Bernoulli's equation, it is assumed the Bernoulli's equation is valid along a streamline of the fluid. See here the streamline, and on the streamline everywhere the fluid velocity vector would be tangent to the line. Based on the streamline definition, we have the mathematical equation for the streamline equation, which is given as this. The velocity vector v corresponding the vector ds on the streamline is 0. This means the velocity vector and the segment vector ds are in same direction or the opposite direction. And this streamline equation can be expressed as this. And in this talk, this streamline equation will be used for deriving the Bernoulli's equation. However, we have also an exception for this assumption, because in the potential flows, Bernoulli's equation is satisfied in the entire fluid field. Thus, there's no limit on the streamlines. To derive the Bernoulli's equation, here the steady Euler equation is given for 3 moment equations as this. And we also term these 3 equations as equation 1 for the first moment equation, and the equation 2 for the second moment equation, and equation 3 for the third equation. Since for the generalized Bernoulli's equation, it is valid only on a streamline, thus the Bernoulli's equation must be satisfy the streamline equation given as this. And in the application, we can either use U to represent V and W from this streamline equation, or we can use V to represent U and W, or we can use W to represent U and V. All this will be used depending on which moment equation will be used. Here in this slide, we look at the first moment equation in the Euler equation given as this. And here we will use the streamline equation given as this. Here V and W would be represented by U on the streamline. So the left-hand side of the Euler equation, the first moment equation of the Euler equation, is given this. And we substitute the velocity V and W into the equation. We have this. And we can take U out of the expression. We have this. Now we can multiply the equation 1 by dx. Then the moment equation would become as this. Or we can write this equation as this. And we can change this into this. Here, U squared. And obviously in this bracket, it is du squared. So we have the moment equation as this. Now in this slide, we look at the second moment equation given as this. And in here, we will use V to represent U and W on the streamline. Thus, the left-hand side of the moment equation would be calculated as this if we substitute U and W into the expression. So we can take V out. Now we can multiply the moment equation 2 by dy. The equation would become as this. And we can obtain this and this. This bracket would be the differential of V squared. For the third moment equation, we can substitute U and V, use the relation this. So we can have the expression as this and this. Now we can time the equation 3 by dz. The equation would become as this. This equation would be very similar to the first two moment equation, but with the extra term here. Minus g means the gravitational force is in the opposite direction of z. So we can write this equation as this, and we will have the expression for the third moment equation. Again, the expression in the brackets would be the differential of W squared. Now we can add all these three equations together for this, this, and this. So we have the expression on the left hand side, this, 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 and this. So we put all this velocity component together. We have this, and take this 1 over rho out of this expression. So we can see in the bracket is actually the differential of pressure. So the expression can be expressed as this. Capital V square is the sum of these three velocity components squared. And this is the differential for the pressure. When we consider incompressible flow, density is a constant. Then we can write this equation as this. The differential of the expression is 0. Integrate this, we have the Bernoulli's equation. Here C is the integral constant. It is the total pressure in the fluid. Now we will see one example for applying the Bernoulli's equation. The question is an water pipe. See this plot with an inlet at A1, R1 equaling to 0.2 meter, and a smaller outlet at A2, R2 equaling to 0.1 meter. The height h is 2.5 meter. Suppose the flow rate is 1 cubic meter per second. The water density rho is 1000 kg per cubic meter. The question is to find the flow velocity V1 at A1 and V2 at A2, and the pressure difference between A2 and A1, P2 minus P1. Solution: we can calculate the section area A1 is given as this and A2 is given as this. Thus, V1 is calculated as the flow rate divided by A1. It is 7.96 meters per second. And V2 is the flow rate divided by A2, given as this. So we have the velocity 31.85 meters per second. Here, when we calculate the velocity V1 and V2, we assumed the velocity at A1 and A2 would be uniform. Thus, we can apply the equation V1 equaling to Q divided by A1 and V2 equaling to Q divided by A2. Based on Bernoulli's equation, we have this 3 times at A1. Because these 3 terms added together would be constant, that means at A1 we have these 3 terms, and at A2 we have these 3 terms. Therefore, we can calculate P2 minus P1 given as this expression. Z1 is here and Z2 is here, so Z1 minus Z2 would be minus h. So we can calculate the pressure P2 minus P1 given as this from this term and this from this term. So it is roughly equaling to minus 500 kPa. So from this calculation, we can see P2 is smaller than P1. It seems this is understandable because P2 is at a higher position. But we must see the contributions of the pressure based on the Bernoulli's equation. This part for the pressure reduction due to the higher position at A2. So it is minus 24,500 Pa. And a large pressure reduction came from this part due to the higher velocity at A2. It is minus 475,000 pascals. The second example for the Bernoulli's equation is the similar pipe, but at A1 we have a smaller inlet, R1 equaling to 0.1 meter, and we have a large outlet at A2, R2 equaling to 0.2. The height is still 2.5 meter, and the flow rate is 1.0 cubic meters per second, and the water density is 1000 kg per cubic meter. And the question is to find the velocities V1, V2, and the pressure difference P2 minus P1. Similarly, we can calculate the section areas first. A1 given as this and A2 given as this. Thus, we can calculate the velocity V1 given as this, so it is 31.85 meters per second. And V2 equaling to Q, the flow rate divided by A2, so it is 7.96 meters per second. So again, we can use the Bernoulli equation. This part at A1 and this part at A2, but they are constant, so they are equaling each other. Thus, we can calculate P2 minus P1 given as this expression. So you substitute the values into this expression. We can calculate the pressure difference P2 minus P1. And now we have positive value. It is 451 kilopascals. So here we can see the pressure P2 is much larger than P1. This is contradicting with our sense. Since P2 at higher position, the pressure should be lower than P1. But based on the Bernoulli equation, we can see the pressure difference is contributed by two parts. A small pressure reduction due to the higher position at A2. It is minus 24,500 parts. And in here, a large pressure increase due to the lower speed at A2. It is 475 kPa. So put all this together, we got the higher pressure at P2 because the lower velocity at P2. So in this regard, the Bernoulli equation would give some counterintuition result. Like this here, P2 is larger than P1. But this is correct. We will see more examples for using the Bernoulli equation in the following talks.